With Vitis, software developers can build custom accelerated designs. For the Vitis software development flow, that is creating hardware kernels using C, C++, and OpenCL, you can use the Vitis accelerated libraries to help build your design. The Vitis accelerated libraries are open source, pre-optimized libraries that you can reuse directly in your own design. Some of the libraries are specific to application domains. These include vision and image processing, finance, data analytics and database, compression, and security. Others are common to multiple application domains such as linear algebra, digital signal processing, maths, statistics, and data management. The full source code for these libraries is available on the Xilinx GitHub. We'll look at the general structure and each of these libraries in more detail. There are three types of implementation provided in Vitis libraries. These are Level 1 primitives, Level 2 kernels, and Level 3 software APIs. The Level 3 software APIs provide C, C++, and Python function interfaces. These APIs are called from host code to interact with the underlying hardware kernel. This allows pure software developers to offload specific accelerated functions to pre-built FPGA images. You may see these pre-built images referred to as overlays. The Level 2 kernels are HLS-based kernels. They are pre-optimized functions that can be used directly to build a hardware kernel. Level 2 code is only for building hardware kernels, so you do need to write and build host code to call and schedule the kernels. The Level 1 primitives are lower-level building blocks. They can be leveraged by developers working on custom hardware designs or kernels. Level 1 primitives are particularly suitable for hardware-savvy designers. Whether you want to accelerate portions of your existing host application or want to develop accelerators for deployment on Xilinx platforms, calling a Vitis accelerated library API or kernel in your code offers the same level of abstraction as any software library. To design custom accelerators for your application, use Vitis library functions as optimized algorithmic building blocks, modify them to suit your specific needs, or use them as a reference to completely design your own. We'll now look at each of these libraries in more detail. The Vitis Vision library provides performance-optimized kernel and primitive functions for image and video processing applications. Library functions include color and bit depth conversion, channel extractions, and pixel-wise arithmetic operations. Geometric transforms, image filters, and statistic generators are also available, and there are functions for feature detection and classification and 3D reconstructors. The libraries also support motion analysis and object tracking. These libraries can scale to meet your requirements. You can configure the clocking or the throughput requirements depending on your application. Vision libraries include a lot of the functionality in the popular OpenCV software libraries with some optimizations and additional features for FPGA. The Vitis database library provides modules and kernels to support data-intensive and compute-intensive database applications. At the module level, it provides an optimized hardware implementation of most common relational database execution plan steps like hash join and aggregation. At the kernel level, the predefined kernels can be used to map a sequence of execution plan steps without having to compile FPGA binaries for each query. The Vitis BLAS library is provided for accelerating linear algebra functions. It supports Level 1 primitives, Level 2 kernels, and Level 3 software APIs. The Level 3 software APIs support C, C++, and Python function interfaces. The library includes general matrix multiply and general matrix vector multiply. This library can be used as a drop-in replacement for the equivalent CPU and GPU-based BLAS operations. The primitives in this library can also be used across other applications. The data compression library is a performance-optimized library for LZ data compression and decompression. At the Level 1 module level, it provides hardware implementations of the core LZ-based and data compression-specific modules like LZ4 compress and snappy compress. At the Level 2 kernel level, demonstrations of data compression algorithms are shown, which internally use the optimized hardware modules. Demos can be used to familiarize yourself with the operation of a library or as a starting point for your own design. The Vitis Data Security Library brings real-time performance to security applications. The Level 1 primitives provide optimized hardware implementation of most common relational security algorithms. Block ciphers, including AES and DES, are included. Stream cipher hashing methods like message digest and secure hash algorithms, including SHA 1, 2, and 3, and Blake 2 and Shake, are all available. The primitive code is developed in HLS C++. Advanced users can easily tailor and optimize or assemble proprietary logic. Benchmarks of different accelerated applications are also provided with the library for easy onboarding and comparison. The Vitis Quantitative Finance Library is intended for a variety of applications in the quantitative finance domain, such as financial modeling, trading, evaluation, and risk management. The basic L1 functions include statistical functions such as random number generator, numerical methods, for example Monte Carlo simulation, and linear algebra functions such as singular value decomposition and tridiagonal and pentadiagonal matrix solvers. Level 2 APIs are provided at the level of pricing engines. Various pricing engines are provided to evaluate different financial derivatives, including equity products, interest rate products, foreign exchange, and credit products. At this level, each pricing engine API can be seen as a kernel. You can write your own host code to call different pricing engines. The Level 3 software APIs hide the detail of data transfer and kernel-related resource configuration and task scheduling. Software application programmers can use the higher-level APIs to run various pricing options without getting involved in the lower-level kernel and hardware details. The Vitis Solver library provides a collection of matrix decomposition operations, including Cholesky, LU, QR, and SVD decomposition, linear solvers, and eigenvalue solvers. Again, the solvers can be used across multiple application domains, including across some of the other Vitis libraries we've seen previously. Lastly, and just to highlight, the Vitis accelerated libraries are licensed under Apache 2.0. This is a quite permissive license. You don't need to pay Xilinx anything for the source code. You can modify the source and redistribute without telling Xilinx, and you're allowed to use these libraries commercially. You can charge your end users for any products derived from the Vitis libraries if you want to. This concludes the Vitis presentation sections. We've covered all the sections listed, from platforms to the Vitis toolflow, design analysis, optimizations, and finished with the Vitis accelerated libraries. The last section will cover PINC for compute acceleration. There are some additional resources you might find useful: the links to the Vitis webpage and the Alveo webpage, and a link to the Vitis accelerated libraries. The Vitis user guide, and I'd recommend that you check for the latest version, or the version that corresponds to the software version that you're using, and also the Vitis AI user guide. I'd also recommend that you take a look at the user guide titled Get Moving with Alveo. This has some examples of writing code for hardware accelerators. And finally, there's a free ebook, Parallel Programming for FPGAs. This covers writing HLS code for accelerators.